The next talk will be given by Professor William Ka-Ming Lau, and he has served as the director of a large climate lab at the NASA Goddard Space Flight Center, and has now moved on to the University of Maryland, serving as a senior research scientist at the Earth System Science Interdisciplinary Center. He will give a talk on the climate observations and modeling future climate change. He has hurt himself during the future, so at his request, I'm letting him sit down.
Thank you. Okay. Well. All right. Well, sorry about that. Too much walking. And so you've heard the perspective from geology and also from archaeology and or anthropology. So I'm going to talk about something that I've been involved in many years in terms of looking at the, shall I say, the modern day Asian monsoon, which includes probably, I still will talk about some history of the monsoon as really relevant to the East Asia here. Go back a little bit, maybe up to the 500, 600 years ago.
Testing. Sorry.
Is it working?
Not loud enough.
How about this one? Is it better? Oh, okay. All right. So, so here's a satellite picture of the Asian monsoon with India right in the center, and all this cloudiness you experience during the monsoon season. So here's a chart that's similar to what Peter has shown. It has added information in it in terms of trying to define the Asian monsoon. So this is the June, July, August average chart of the streamline flow, indicating the wind direction. As you can see, the monsoon encompasses winds which generally, if you look at the region, let's look at the pointer here, okay. So this is a southwesterly flow. This is the Somali jet. So we are interested in the Asian monsoon. In fact, the Asian monsoon is much broader. As I will show later, it has very strong global contact in terms of how the global circulation can affect the monsoon, and the monsoon can affect the global circulation. But here, in this region, we're interested in the summertime southwesterly flows across from the Somali jet, India, Indochina, and then up the Hong Kong, East Asia here, so southwesterly flow. And so the monsoon is by no means a fixed pattern. Within the monsoon season, June, July, August, there's a lot of variabilities in terms of monsoon variability. For example, in the East Asian region, many people probably heard about this, is so-called the Meiyu front, the Meiyu or Baiyu front, which is the heavy rainfall. In fact, it moves, its position, this is just the mean position in June, July, August. In fact, if you live in Hong Kong, you know that this Meiyu front actually is very active around early part of the monsoon, which is in April, May. The Meiyu front is actually stayed here. And then in around June, it comes up to the Yangtze River. And then in July, August, it moves up to Korea and Japan and Beijing, northern China. So this is what we call, and the movement is not smooth at all. It's like a jump. So there are, people talk about the three positions of the Meiyu front. The early one, the June, which is right now, and then July, August comes up that region. So it's just like pop, pop, pop like that. So it's a sudden jump phenomenon. So that's very complex, although this is kind of misleadingly simple. So then this is right in the East Asian side. And of course, I'll focus more on the Asian side. The Indian side is different story. It's a somewhat different story because both of them are affected by the Tibetan plateau, as has been mentioned. East Asia is downstream of the westerly flow of the Tibetan plateau. The Tibetan plateau really blocks the northward flow from the Indian monsoon, okay? And so we have the variability of the main front, and then we have a lot of something called intraseasonal oscillation, which now we know has a prominent time scale about, sometimes we call it the biweekly time scale. Those give you rain and dry spell in the Indian region, in southern China and central China. And we all know in monsoon region, rain doesn't come all the time, June, July, August. It is very intermittent. But this intermittency actually have some periodicity in terms of how things happen. And a lot of the research in monsoon is trying to understand this kind of periodicity, because it does help the daily planning, in fact, or weekly planning in terms of we expect rain or not. So those are on top of that. And then this is part of the monsoon also. I mean, you include the Asian monsoon, would be around the equatorial region, something we call the Julian oscillation, MJO, is a very prominent oscillation in the tropics. And this oscillation actually goes all the way around the globe, okay? And in fact, the June-July season, it acquires extra characteristics and become interactive with so-called northward movement of the monsoon in that region. So, and then during the later part of the monsoon season, we all know that we have typhoon. I mean, starting from August, September, October. So the monsoon interact with the typhoon, obviously affect the Hong Kong region. So if in a very broader context, monsoon has a lot of weather phenomenon associated with it, has to do with the shift of the Mei band, the typhoon, and many things all the way. And in fact, the monsoon, there are other regions of the world that have monsoon as well, like Africa. I think you will probably hear a little bit later on. West Africa and South America, all of them. This is far the most extensive, because usually when we think about monsoon, it's probably within in the tropical phenomenon within plus or minus 30 degrees. Asian monsoon, because of the particular geography, extend all the way up to 45 degrees. That's why in Japan and Korea, you also have a monsoon. And in fact, the monsoon characteristics has a lot of influence. It's no longer a tropical phenomenon. It has a lot of influence from mid-latitude. So that's sometimes we call it hybrid monsoon. But that's the entire complexity of the monsoon area. So I want to say something about the monsoon. It's actually derived from Arabic, the word masam, which means season. So there is a very definite transition in the season. If you look at June, July, August, the mean picture is southwesterly flow. If you look at the JF, it's more or less, of course, it's not the same, that you just change the arrow direction. And then it flows northeasterly, like this. Okay, this is southwesterly and northeasterly flow. And in fact, this change in wind direction are well known earlier. This would be like in the early 1200 or something like that, where early Arabian seafarers know about this change in wind, and they may use them for navigation. One of the most famous in China is Cheng Ho. Many of you know, you heard about him, okay? And in fact, his origin, Arab, he's an Arab. He's Muslim, and his great-great-great-grandfather are from Iran, okay? That's the history. That's Cheng Ho. He is, in fact, linking back to the Mongols actually took over all the way to Baghdad and took over Iran, and then took some of the Arab people together with them, and they ruled China. And Cheng Ho's father is a governor of the Yunnan province at that time, so and he's Arab by origin. So he has that seafaring nature. And in fact, many of you know when the Ming dynasty has come, they purged the Muslims. He was captured, and he was option on him for him to serve with the king. So that's very famous. Cheng Ho, 1370 to 43, and he has this famous 7th expedition to Southeast Asia, East Africa during the Ming dynasty, way before Christopher Columbus sailed, almost 70 years before. So that's very famous in Chinese history. And then if you think back about more quantitative study, the first study of monsoon dates back to Harley, 1686, this Englishman. George Hadley, also an Englishman, 1735. And so modern day study of monsoon started from Sir Gilbert Walker, 1868 to 1958, and he actually discovered the southern oscillation. Now we call it Walker circulation, which is an east-west, I'll show you later, an east-west circulation that links the monsoon system, mostly India, to the pressure changes way over in the eastern Pacific in the Tahiti. It happened to be a weather station, and use that information, statistical information, to predict Indian monsoon. With not a whole lot of skill, but there seems to be some information. So that's kind of the history, which is interesting. Just to show you, this channel is for real in history, and this is his route, his 7th expedition. And it's known that he knows about the change in the wind because he has to go this direction. So each time he sets sail, it's always in the winter. He will never set sail in the summertime. It goes against the wind. So he knows about that. How he knows, we don't know how he knows about this wind, all this wind direction. I mean, where he got the data, but he knows that. Maybe by trial and error. When it starts in July, he'll never get very far. So he just followed the northeasterly flow, monsoon flow, all the way from I think some part of China or central China, just go through it to the Malacca Strait, come through here, and 7 expedition, 1, 2, each time get further than the other, 1, 2, 3, 4, 5, 6, 7, all to the east coast of Africa. And some of you probably also read about this novel by Gavin Mansey, actually wrote a book about and claimed that Chang Ho actually sailed much further than this. He actually rode around the Cape, the here, and all the way come up and actually come to the Arabians. And he showed that, of course, that's also. So that's one of them. And then this one is Sir Walker, who is the first a director of the meteorological department. And I talk about the southern oscillation. So here is this is the southern oscillation. So India and monsoon is right this region. So then he find out again using, this is a modern day picture of this southern oscillation. And he shows that the pressure difference between somewhere in Tahiti and Darwin actually goes up and down now this is a modern day rendition. At that time he only had two weather stations, and he looked at the correlation. And it turns out, as you can see, this up and down pressure difference actually touches somewhere in India. So he used that to predict Indian monsoon. And that is documented. He wrote papers on it. He died in 1958. So that's kind of the interesting history. I thought you may be interested. I'll talk a little bit about the critical timeline in modern era monsoon research. So you got to have an idea of how monsoon scientists do their work. So basically, I'm just looking at about 10 years of time scale. Each time, I mean, this thing is not, it's just kind of cumulative, okay? The timeline is that everything is more cumulative or replacement of some old stuff. So it just keeps adding on more and more. By the time we are here, we have all this previous stuff, improvements of things like that. So 1950, I would say the modern study using observation from global radiation network, that was just the time where Sir Gilbert Walker was at the kind of the later part of his life, where this thing started to have the global radiosonde observation, the balloon observations. And in the 70s, there's a global general circulation model start to use. So this will be used mathematical, physical equations where you put in the hydrodynamics in the rotating sphere, very fundamental, rigorous mathematics and physics. You build this general circulation of the large-scale monsoon, and then in the 80s, we start to have satellite observation, okay? And then up to now, of course, we're much better at satellite observation, and then start the idea of data assimilation. Because in order to look at the whole weather system around the world, you need to look at observation from the radiosondes. You need to look at ground observation. The satellite observation helps you. You also need the model. So the assimilation is a process where you basically blend the information from the physically based models to observation and try to describe the climatic states of the world in a dynamically consistent way and consistent with observation. So that's a very elaborate process. Nowadays, there's still a very active branch of atmospheric science research. That means data assimilation. You assimilate real data into a model and then get consistent results. And the 90s, then we start to have coupled, this is mostly atmosphere, coupled ocean, land, atmosphere, global models to study the global monsoon system. In the 50s, so this is a long period of development. Now we have this. And of course, in the 2000s, all this we are incorporated. Now this is something called Earth System Model. So now you're going to incorporate the carbon cycle, and some more advanced one have some simple biogeo cycle in it. So you're including other branch of science into it, physics, and here you actually have a lot of chemistry into it now, just atmospheric science, oceanography, and hydrology, all this included. So Earth system science, and then was because these models are huge, you need supercomputer to do it. So sometimes you're simply interested in a certain region, you use this approach called downscaling, using high-resolution regional model. This one you build all the physics of the model by observation, and then you use that to do what we call parametrization. This model, the physics. And then cloud resolving models would be very high resolution model, in fact, of the scale. This one, when the first models are built, so all them with 5 to 10 550 to 100 kilometer, it's 500 kilometer, 100 to 500 kilometer. Now the cloud resolving model can be down to 1 kilometer. This is very high resolution, and right now even the most powerful computer cannot afford to run cloud resolving model at 1 kilometer globally. It's just too much computer time. It will suck up, and you run a day of simulation, it probably take you 3 days of computer time. So that's not that's very high resolution. And of course now we are at the stage where we're talking about expanded monsoon research. It is very multidisciplinary. You heard about geology, information archaeology. Sometimes we call it interdisciplinary because you never thought this would link up with, for example, archaeology, but now it is there now. It's policy relevant studies because you have to do simulation. Do scenarios. That is what the IPCC is about. They use scenario. In fact, the IPCC models are run at much lower resolution than some of the scientific study that we do at high resolution and all. And then now we have super high performance computer, and then we have big data because now you generate so much data in just running the model output. Of course, we have all observation too, satellite observation from NASA. I used to work for NASA, and we know that we are generating huge amount or terabytes of data, and everything. So all this we're dealing with big data and everything. Okay. So next. Okay. So I think I quickly move on. So here is an example of what we are worried about. Is that this is the CO2, the CH4, and the N2O kind of variation for the past 2,000 years. This is much shorter period than before. As I've said, the CO2 amount in the Earth has experienced similar level CO2 before, but that would be many, many years ago. And the spectacular thing about this is at the time, the rate of change last 100 years has been spectacular. That rate of change has never been seen before. Okay, that level has been before, but over thousands and thousands of year time scale. But this is the fastest we have ever known, and this is all this gas, CO2, CH4, or from human activities into source. And so I'm going to quickly, many of you heard about greenhouse effect. Basically, if you have a lot of CO2 and greenhouse gas in the atmosphere, the way that the Earth is heat is by the sun coming in and going, the clouds reflect solar radiation, but most of it is come through and then heat the Earth. If you have greenhouse gas in between, what happened is that the greenhouse gas would actually, then it would be, the Earth will cool off by outgoing long-way radiation because it warms up and it cools off. But if you have a lot of greenhouse gas here, this cooling rate will be reduced. In fact, the greenhouse gas will, here it shows the greenhouse gas actually produces a strong warming effect. So that's why it's called the greenhouse. Basically, greenhouse, you block off sunlight and you block off the cooling effect. So it's just like a blanket, you just keep it warm. It's already hot here, but you put a blanket on top, you get more sunlight and you get it hot. The scientists have at all the gases that produce a warming effect. As you can see, CO2 is the tallest one, that is most important. But come to all this called the short-lived gas, the CH4, NO2, all are actually very considerable amount in terms of heating rate. So by this way, and then as there are actually some substance in the atmosphere that actually produce cooling rate. This side, the barcode, this side cooling rate. This turns out to be aerosol clouds actually produce cooling rate. And I don't have the time to go into the effect. So as you can see, the atmosphere have all these mostly heating agents and cooling agents, And by the time you kind of add up all this and find out, you will find out that at the total heating of the atmosphere, this is the way you see it. In the 1950, the total atmospheric heating is around here 0.5 watts. Now in the 80s, it's about 1.5 watts. In the 2000s, it's about 2 watts per meter squared. So that's steady increasing. That is the overall greenhouse effect. So it makes the temperature warmer. Okay? There's no question that the temperature is warming, and global warming. The IPCC said this is unequivocal evidence that the whole world is warmed and can be attributed to this effect. That's a simpler picture. That means, okay, so I think most scientists will agree with that. But what most scientists is still debating on is that how does the water cycle change? How does precipitation change? Here I'm going to show you some more recent results to give you an idea, and some of that work is done. I did, our group did, and other people too. So I'm going to try to summarize in terms of there is now, people are thinking there's a fundamental change pattern in the global water cycle in a warmer world. In fact, this warmer world could be natural or could be man-made. We don't know, but this idea that there will be, instead of saying total changes, idea that there will be more extreme precipitation events, and at the same time, so I'm going to see if you recognize like the Bakwa, okay, something like that, which is yin and yang part. So I just purposely put it. If you're Chinese, then you understand what I mean. There's an equilibrium has to be set up between the wet part and dry part. If you shift that equilibrium by greenhouse gas, this equilibrium will change. And in fact, it's even worse than that. There are and the regions are not mutually exclusive. There are certain regions in the world that is what we call a transition region that experience both extreme heavy rain in the wet season, and at the same time they experience drought in the drought season. They can hit on both sides. Okay, think of that concept. It's very important. This is how the global water cycle can just climate change as a consequence because the last region respond. So you can imagine the semi-arid regions dry, but at the same time it's going to hit by heavy precipitation. I cannot prove it, but I can think of an example of Texas recently. They have been drought for that many years. All of a sudden they got heavy rain. Either way, you cannot use that water. If you are drought, you cannot use the water. If there's too much extreme rain in the wet season, you cannot use it. So where can you find the water? So that's a very, very important concept in terms of water cycle. And that is the prime information. Even in the monsoon region, it will be more or less following. And that's my personal opinion. It's very important in the monsoon region that you recognize that there's no contradiction in terms of certain regions having heavy, and at the same time, not at the same time, during the dry season, they will get drier. Okay. In fact, we have a theory. In terms of large-scale picture, not specific to the monsoon, is that this is a recent paper published in the National Academy of Sciences by myself and a colleague. Basically, I simplify it. In the present climate, we have the so you think the equator, this is the polar region, and this is the mid-latitude. So the monsoon region is right between the equator and the subtropics. So in the present climate, we're rising motion in the warm part in the tropics, and sinking motion in the mid-latitudes. This is the subtropical jet stream. Then you have the tropopause. That means this is the most of the active weather takes place within the troposphere. So your rising motion, motion. This region will be the desert, mostly subtropical desert regions. Okay, and then this would be the polar front region. This would be mid-latitudes. Okay, so you can figure out the monsoon region is probably around here. Okay, but this is a zonal average picture. Simple. Okay, very clear. In a warmer climate, what happened is that generally they're uneven warming. So you have got warmer climate along the tropical region, and this warmer climate and more moisture promotes increased rainfall. Increased rainfall comes in the form of enhanced deep convection. So this is drawn. This clouds becomes deeper, But at the same time, it is narrower. The clouds actually get narrower in this region. And while the rising air becomes stronger and stronger, it pushes upwards. So the tropics become deeper. And as a result, it becomes deeper. The sinking motion part actually become much wider. And you can see, I draw it over here. Now it's going to shift it into this region. So you can see drier area develop first. This is almost counterintuitive when we get this result. Here what we are seeing is that in a warmer and wetter world, with overall that's the case, you're actually going to see drying signal first in part of the tropics, especially over land. You don't have time to explain why. And also in the drying region. And in fact, if we do a signal to noise ratio analysis, this part is where this signal starts to emerge as the warming signal, not the precipitation, because it's very difficult. Signal to noise ratio is very high, very low in the precipitation region because precipitation goes up and down like that. While drought tend to be broad and long, and if it comes in, it tends to stay longer. So from that sense, that is what we are seeing from a global perspective, and the monsoon is part of that global pattern. So when we look at the monsoon climate change, we have to have that concept in mind, is that that is what's happening. And I'm actually going to skip that part because this is industrialization in China, and there's some information I got from the Beijing climate report. So from a global warming perspective, China has, this is from their report, for more than 2 degrees since 1900. This is the 2 degree, but it's regional, not the global. The global 2 degree will have implication. If global warming reached 2 degree global, increased by more than 3.5 degrees per decade since 1980, and 30 to 50% increase may have been masked by aerosol. That is a very important part. Aerosol, in a way, is a bad, okay, it's to health, but from a global climate point of view, it is actually trying to mask some of the warming because of fact. So you really have to do. We all know that we want to clean up the atmosphere, but you have to also clean up this consequence that you will see more of the global warming by CO2. You have to decide what to do in terms of how you, that's a policy issue. So there are the other things that could be talking about the abrupt change. They are in the extratropical near polar region. We have something called a permafrost. This is a region of constant frozen ground, very, very hot, very cold area. But if this area also gets global warming, it would release what is called methane underground. And this methane can really speed up global warming. And that is where you're going to get an abrupt change, climate change happen. Right now, thermal force in China, they estimate that has shrunk by 5 to 10% in the last 30 years. And I know there are some observations showing that there's already increased CH4, the methane in the atmosphere. Temperature in Asia will this is model prediction, additional 3 to 5 degrees in the 20th century, depending on various emission scenario, even stabilization. And even if we were to stabilize CO2 at 450 parts per million by 2050, the problem is this temperature will have a delay effect. It will continue. So we have to tell politicians that this is a difficult problem. If you do it now, this temperature warming will continue for the next 100 years. But if you don't do it now, it will never work. So that's the message. So I think I'm going to stop here. It's just simply a picture saying that I already mentioned that generally we get more rain, but as I said, this drought business is there, and then you will see rain and more drought, and the circulation is adjust, and most of that it will be winter, but there are other regions is warm. So I think we will stop here. I mean, here we have to deal with, if we know it's warming, so we have to deal with all these hazards, flood, melting of glacier, smog, air pollution, tropical cyclones, typhoons, damage, and the biomass spreading, and all this this is part of the system of the natural and human system, and as climate change comes, they all adjust. Some human will adjust, but who is going to win out? We don't know. I mean, so we're talking about the global atmosphere adjusting. Humans are all adjusting all this global force, and I think I'm going to here. This is kind of the